Today we'll discuss about three topics. First, we'll discuss about reinforced concrete problem. So you may have seen concrete construction site where you have quite thin steel road, and we call that as like a steel reinforced concrete, or in Korean 철근 concrete. And we're gonna discuss about mechanics and design of such structure. And in the second topic, we'll talk about eccentric loading of a symmetric member. In eccentric loading, we're not gonna consider pure bending. So here we're gonna consider the case where we have both N and M are non-zero and T and V are zero. As a third topic, we'll talk about asymmetric bending. So let's begin from the reinforced concrete. So to discuss about reinforced concrete, we have to think about the necessity of using steel reinforced concrete, or in Korean 철근 concrete structure. When we consider the strain curve of concrete and rocks, we're gonna have hugely asymmetric response under tension and compression. Actually, concrete and rocks sustains compression very well when strain is negative. You can see that it can sustain quite large stress until the failure. However, under the tension or when strain is positive, the maximum strength is about 10 to 20% of ultimate strength under compression. So, in conclusion, in short, concrete is very weak in tension. So how can we reinforce the concrete? Okay, so the idea behind here is use the steel rod. Okay, so when we have concrete, we can have steel rods, so that we use the advantage of concrete and steel together. Okay, why steel? Because steel has several times higher stiffness and strength compared to concrete, and only with small cross section it can sustain much larger tensional loading. So, but somebody may ask why we don't use 100% steel. Because for the same cross section, steel is much heavier than concrete. Unless we're gonna build some like a glass house with really thin like a I-beam steel. If we just want to consider like a regular building with a regular size of window, with okay level of thermal insulation, we need concrete, right? So if we build really thin building only out of the glasses and like a really thin steel beam, we're not gonna have good enough thermal insulation. And also if we make the building too thin, it'll be quite weak under the earthquake. Okay, so we anyway need a little bit of volume and mass based on concrete. Okay, however, if we use like a 100% concrete as in the Roman and Greek buildings, we have to use really thick structure, and we can have very small space for windows. Okay, and if we combine steel, we can somehow reinforce the weak tensional part of the concrete using small volume of steel. And another disadvantage of using only steel only structure is that if we have like quite thin rod, it can buckle really easily. Okay, so we don't want this thing happen in our building. So the idea is let's try to mix concrete and steel, and this is the the kind of composite material that you're gonna see most modern building in Korea. So when designing concrete and steel structure, reinforced concrete structure, and for a conservative design, what you can do is we simply assume that concrete does not sustain tension at all. And if we make this assumption when making a design, then it will force engineers to use enough steel to sustain entire tension, even when a complete crack appears in concrete. Okay, so when you look at like an apartment in Korea, like like a 30-year-old apartment and like 20-year-old like business buildings uh, in like a Korean downtown, you might see like some crack happens in the concrete. Okay, but even though you see cracking there, you don't need to worry about the safety of the structure, because even though there is crack, the compressional part will still works fine for concrete buildings. And even though there is crack, I think the buildings are constructed such that still can sustain the entire road, even in the you know quite large cracking in concrete, so it will be still safe. Okay, so and also it's mathematically simple. Okay, so in our class ME231 yeah, I will consider the case when we design the reinforced concrete. We'll completely ignore the tensile loading capability of concrete and rely 100% you know tensile loading on the steel, and based on that we'll suggest a design guideline. Okay, so let's consider this example. So in this example we're going to consider cross section of reinforced concrete, and the width is b, and the distance between top and the location of steel is given as d, and x is the unknown number. This is the position, the distance to a neutral plane from the top. Okay, and we'll consider total area including all three steel beam as area of steel as. Okay, so the question we can ask is, where is the location of a neutral plane? Only after obtaining the position of neutral plane we can think about I and application of flexure formula. Okay, so idea behind it is we have to first find equivalent homogeneous material problem, and we're gonna make equivalent homogeneous material problem with concrete. So as I told you, it will ignore the role of concrete below this neutral plane, so we completely ignore the contribution of concrete below the neutral plane, and above we have the concrete part as it is. And if we consider the ratio between steel and the concrete Young's modulus as n, then we replace the steel rows with n times as area, quite thin area. Okay, and as you can see, because we are ignoring these part of concrete completely, we don't have any information about this area. Actually we don't need. Okay, so given this equivalent problem, considering zero tensile loading capacity of concrete, then we can think about the definition of a neutral plane and try to obtain the x. So how can we obtain neutral plane? So integral yda equals to be 0, and to obtain this integral, we simply obtain area of top body, which is b times x, and we know the location of this guy, which is x over 2 for rectangular space, and we have area n times as at the bottom, and we have the distance to y equals 0, which is a minus d minus x. Okay, so with this, we have to satisfy these summation to be 0, because we are looking for y equals 0 neutral plane position. Then after massaging this equation, we're gonna have a second order equation regarding x, and if we solve this for x, then we can locate neutral plane location. X is the distance from top to neutral plane. So this is abstract approach, and let's try to solve a concrete example. I mean not concrete, but more specific example with real numbers. In this problem, you have to consider maximum stress in steel and maximum stress in concrete for this cross section, and the Young's modulus of steel and Young's modulus of concrete and the applied moment are given as follows. Okay, and the distance from top to steel load is 100 millimeter. The entire height is 140 millimeter, which is not necessary information as I told you. And the width of this reinforced concrete is 300 millimeter. and the diameter of steel is given as 16 millimeter, or because we have this diameter and the radius is 8 millimeter, because we have radius for each one, for two steel, we can obtain AS by obtaining 2 times pi r square, 2 times pi times 8 square, which gives us a 4 or 2 square millimeter for AS. And regarding the ratio n, we have 200 divided by 25, which is 8. Okay, so if we plug these numbers into the equation that we just obtained like 1 minute ago, yeah, let's starting from this information, we plug in B equals 300 millimeter and NAS equals to be 8 times 402, yeah, and this is 8 times 402 times, yeah, D is 100. D is the distance to the from the top to steel rod. Okay, and we ends up having X equals to be 36.8 millimeter. Now, if we convert this to equivalent concrete problem, yeah, we have this. Yeah, so the distance to the neutral plane from the top is given as 36.8 millimeter. Width is 300 millimeter. Distance to steel is 100 millimeter. And we have the distance to the steel beam, which is 63.2. Yeah, this is obtained by 100 minus 36.8. Okay, now the area of this guy is n times AS, turns out to be 3216 square millimeter. Okay, so in our next procedure, next step is, after obtaining the centroid, is to obtain I with respect to this plane. Okay, so regarding the upper part, this part, we first obtain the area moment with respect to centroid of itself. So we have the equation, which is 1/12 times area times this height squared. Okay, so we have this number. Regarding this parallel axis theorem application, we know the area AC, concrete area, which is 300 multiplied by 36.8 square millimeter, and DC is 36.8 divided by 2. Yeah, this is distance to centroid of this upper block. Okay, so that's why we have this factor of 2 here, factor of 1/2 here. So we ends up having these values. And regarding the area moment of inertia with respect to of its own centroid, of course, there is width, we have 60 millimeter, but typically we ignore this contribution, because when you consider AS H square 1/12, and if we compare this number with that number, it's much smaller than this number. So in most our homework and sample problem, we ignore area moment of inertia for steel with respect to centroid of itself. Then we consider this part, n times AS. This is area of this entire widened steel part, and we have ds squared, distance to centroid, which is 63.2 millimeter square. So we obtain the contribution here after ignoring this. Then we obtain I as 1.78 times 10 to the negative 5 meter to the fourth power. Now, after obtaining these values, we can obtain strain distribution, which is a simple linear function in y, and y minus y over rho, and 1 over rho can be written as m over e of concrete multiplied by I. This is expression for strain. If we multiply EC, we can obtain the stress distribution in concrete. If we can obtain n times EC or ES, after cancelling out EC, we have n times YM over I. Now, we have some numbers from the question. We have numbers here. We have numbers, 36.8, 63.2. After plug these numbers here, and I is from the previous page. Yeah, we found that maximum compressive stress in concrete is 12.9 megapascal. Maximum tensile stress in steel rod is 177.8 megapascal. Okay, so with this, we can finish our discussion on design of reinforced concrete. Okay, so by making simple assumption that concrete cannot sustain tensile loading at all, we can make the problem mathematically simpler, and we can also achieve really conservative design for reliable structure.